All right, welcome. Today we're cracking open the toolbox of mathematics, and trust me, we're going to pull out some of the most powerful and honestly elegant tools you'll ever get your hands on. We're going to build this geometric toolkit together, starting with an idea called similarity and building all the way up to one of the most famous theorems in all of history. Ready? Let's dive in. So let me start by asking you something. How can a simple map on a piece of paper, how can that accurately represent an entire country? Or think about a tiny blueprint for a massive skyscraper. I mean, they're obviously not the same size, right? But they are the same shape. And that idea, it's literally everywhere. It's all powered by a single, beautiful mathematical concept that we're about to add to our toolkit. And the answer? It all comes down to geometric similarity. This is the very first tool we're putting in our kit. And it's a simple one, but it is so powerful. It's just the principle of scaling things up or down without messing up their shape at all. Okay, so let's get a closer look at this. I want you to think of this first tool, similarity, as a kind of perfect magnifying glass. You know? It can make things bigger or smaller, but it never, ever distorts the image. All the proportions, they stay exactly the same. So here's the official definition. Two shapes are similar if you can take one and scale it by some fixed ratio, and it becomes a perfect copy of the other. To put it simply, they're the same shape, just maybe not the same size. That's it. And you know, the rules for similarity, they're surprisingly simple. For any two shapes to be officially mathematically similar, you just have to check two things. First, all their matching angles have to be exactly the same. And second, the ratio between all their matching sides has to be constant. And that constant, well, we call that the similarity ratio. All right, let's grab our next tool and see how this all connects. Because once you know two shapes are similar, you unlock a whole new set of rules for measuring them. Let's call this one our proportional ruler. It lets us predict exactly how things like area and volume change when a shape gets bigger or smaller. So just imagine we've got two similar shapes. And let's say the ratio of their sides is m to n. What does that even mean? Well, for example, maybe one shape's sides are all twice as long as the others, so the ratio is 2 to 1. The big question is, how does that affect things like area or volume? And here is where it gets really cool. The lengths and the perimeter, they scale by that same m to n ratio, just like you'd expect. But look at the area. It scales by m squared to n squared. And volume, that's even crazier. It's m cubed to n cubed. So the big takeaway here is that this isn't a simple one-to-one relationship. If you double a shape's sides, you don't double the area, you quadruple it. And the volume goes up by 8 times. It's huge. Okay, so this is all great in theory, but how do you actually prove two triangles are similar to begin with? I mean, you don't always have every single measurement, right? Well, luckily for us, there are a few powerful shortcuts, kind of like a diagnostic checklist. There are 3 main ways, 3 tests really, for proving triangles are similar. Now, if you've studied congruence, these letters might look familiar, but the rules are a little bit different here. We've got side, 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 angle, and angle, angle. First up is SSS, or side, side, side. This one's the most straightforward. If you can show that the ratio for all 3 pairs of matching sides is exactly the same, boom, the triangles are similar. You don't even need to know the angles. Next up, we've got SAS, which stands for side, angle, side. For this one, you need 2 pairs of sides that have the same ratio and this is crucial, the angle between those 2 sides has to be equal. That angle in the middle is the key. It's what locks the whole thing together. And finally, my personal favorite because it's usually the easiest, AA, angle, angle. If you can prove that just 2 pairs of matching angles are equal, that's it, you're done. The triangles have to be similar. And why is that? Well, think about it. If 2 angles in a triangle match, the third one doesn't have a choice. It has to match too. Okay, let's reach back into our kit and grab the next tool, the drafting compass. This one is all about a really powerful connection between similarity and parallel lines. It's going to let us make some very precise and honestly pretty cool deductions. So here is a massive visual clue you should always be on the lookout for. Anytime you see a line drawn inside a triangle, and that line is parallel to one of the other sides, you have just instantly created a smaller, similar triangle that's nestled right inside the big one. It's like an automatic similarity generator. And this leads us to a really fantastic shortcut. It's called the midpoint connector theorem. Check this out. If you find the exact middle point of 2 sides of a triangle, and draw a line connecting them, that new line you just drew is automatically parallel to the third side. And even better, it's exactly half the length of that third side. How cool is that? A super handy tool to have. All right, it's time. Let's take everything we've learned so far, all these tools, especially what we know about similar triangles, and let's build the master tool, the absolute cornerstone of our geometric toolkit. In fact, the proof for it actually relies on the similarity stuff we just talked about. We're finally adding the right angle wrench to our set, the one, the only Pythagorean theorem. Now, the setup here is very specific, but it's super simple. This famous theorem only works on right-angled triangles. So the two sides that meet to form that 90-degree corner, we just call them A and B, and that long slanted side, the one opposite the right angle, that one has a special name. It's the hypotenuse, and we always call it C. So for literally centuries, people knew there was some kind of beautiful, predictable connection between the lengths of these three sides. A secret equation that works for every single right-angled triangle in the entire universe. So what is it? There it is, a squared plus b squared equals c squared. So simple, right? But unbelievably powerful. What does that actually mean? Well, it means that if you could draw a square on each of the two shorter sides, A and B, and then you added up the area of those two squares, that total area would be exactly the same as the area of a bigger square drawn on the hypotenuse, C. It's a perfect balance, and this works every single time, for every right-angled triangle. No exceptions. And get this, it's not a one-way street. The theorem works in reverse too. So if you just have some random triangle, and you measure its sides, and you find that they happen to fit the formula, a squared plus b squared equals c squared, then you know with 100% certainty that it must be a right-angled triangle. It's a great way to check. So there you have it, your complete geometric toolkit. We started with a simple magnifying glass of similarity and built all the way up to the powerful right-angle wrench of Pythagoras, each tool building on the one before it. So the next time you see the shadow of a tall building stretch across the ground, or you unfold a map, I want you to think about these tools. What unmeasurable heights or what hidden distances all around you can you finally figure out now?